Hello everyone, and this video I'm going to demonstrate some example of calculated work by dark product. Okay, and last time we say if we want to calculate the work in general case, you should use the dot product first times this first vector dot product to the displacement vectors. Okay, so and okay here in here the dot product, like I said, the definition of dot product, I should, I mentioned in last video. I just write down the video. If you're doing a dot product, sorry, a dot product b is the magnitude of a times magnitude of b and times cosine theta. Okay, that's a dot product. But here I want to show you, if we use a component language, what the dot product will be. Okay, so let's suppose suppose here we say that the a vector, and we use the component language, x component of a, and it's a unit vector I plus the y component of a and unit vector j, and z component of a and unit vector j. And here we also have another vector b. It's bx, by, and bz. Okay, plus and the unit vector j, and unit vector k. Okay, when you want to use the component language to the dot product, what will happen? A dot b will become like this. Okay. Okay, first of all, write down the vector a r. It's very time. It's really spend lots of time to write down this dot product bx I plus by j dot plus bz k. Okay, so what will we do? So what's the result by using the component language to do the dot product? So the same thing as you doing the multiplications, but it's we have added a little difference. Okay, first of all, you just use the same distribution law. This times this, this times this, this times this. Okay, what will happen? It will become ax. Okay. I should change the color. Okay, what will happen? Okay, so when you do the multiplication, so first term axi dot bxi. Okay, axi a dot bxi and plus axi dot byj plus axi dot bzk. Okay, so how to do what's the following? Okay, so when you do this dot product, okay, and it's a component. Okay, you just multiplication of a component. Even this component could be like I say, could be a constant or could be a function. Doesn't matter. You just do the multiplication of component, multiplies the component, and then leave the dot product between the unit vector. Okay, for this one is the same, just doing the multiplication of component and leave the dot product to the unit vector. Okay, this also a same thing, doing the component product and leave the dot product to the unit vector. Okay, so for the unit vector, there's a property for unit vector, like I say here. If the unit vector the same direction doing dot product, the result is 1. Like I dot I 1, j dot j 1, k dot k, the answer is 1. But it's in the different direction. Okay, different unit vector dot doing a dot product, they always be 0. Okay, because these two different unit vector, that means they are perpendicular to each other. So that's why their dot product always 0s. Okay, you can check this by yourself. Okay, it must be 0 using this formula. Okay, because when these vectors, they are perpendicular each other, so their theta is always 90 degrees. So their different unit vector, the dot product is always 0. Okay, So the same unit vector doing a dot product, it always becomes 1. Okay, so we take this property. So you will find, okay, this different unit vector. So this will become 0. This different unit vector doing dot product also is 0. So you will leave the ax bx and I dot r is 1. So in the answer, if you're doing this, the first distribution, you will get ax bx. So at the same time, you can do the distribution of ay to this, and this. If you do the same thing, you will get the answer ay by. And you do the same distribution on the azk to this b vectors doing dot product, you will find your answer will be az bz. Okay. So by using the component language, you will see when you use component and language to doing a dot product, the result is just the multiplication of each component. Ax times bx, ay times by, plus az times bz. Okay, and easy to remember, right? Okay, if you're using the component language to doing a dot product, it's just the multiplication of the component, and add them together. Yeah, multiplication of component and add them together. Okay, so practice by yourself. Okay, practice by yourself, and we will use the example from the textbook to do this to let you familiar with this process. Okay, so I will switch to the next slide. Okay. And this example you can do it by yourself. I want to show this example. Is example 6.3 from the textbook. So he says that there is a tugboat. Okay, tugboat is here. Okay, tugboat. Okay, is so I make the tugboat. It's a tugboat. It's this one. Ooh, this is tugboat. Okay, it's a tugboat. Tugboat, if my memory is right. Okay, this is a tugboat, and he's pushing a boat. Okay, pushing a ship. Okay, and ship. Yeah, he's pushing a ship or something. Okay, the ship is here. Okay, it is a tugboat. He's pushing the ship, and its force is and the force done by this tugboat is the the problem says it's it's 1.2 mega I and plus 2.3 mega J. Okay, here's the force exerted by tugboat, and he found the ship that the displacement of the ship delta R is the displacement of ship delta R is 380 I plus 460 J. Okay, and its unit is meter. He's trying to find out what's the work done by this tugboat, right? Let me check. Is this a problem here? He's asking the calculation of work. Let me see. Let me check this. Yeah, the work between the tugboat. Okay. And also want to know the angle between the force and the displacement. Also, what is theta equal to what? Okay. So because this problem, it gives you the vector of force and vector of displacement. So you have to use a dot product. Okay. So like I say, work is equal to the force times dot product to displacement. Okay. So it will be the 1.2 mega I plus 2.3 mega J, and doing a dot product with your displacement vector 380 I plus 160 J. Okay. So like I say, so this too is a component expression of the vector. So when you use the component expression of a vector and doing a dot product, what's the answer? Yeah, you just say that it becomes to the component multiply the component. So it will be component multiply component, component multiply component. Okay, so the answer would be 1.2 mega times 3.80 plus 2.3 mega times 460. So what's the answer? What's the answer? Ah, I didn't write here. Let me do the calculators. 1.2 times 380 plus 2.3 times 460. So it's 1514. Okay, 1514. The answer is 1514. Should I use the bright color? One. Okay, it's my pink one. 1514, and its unit. It's mega joule. Okay, it's because there's a mega here. Mega, yes, and Newton times meter is joule. Okay, and the other problem is you want to find what's the angle between the force vector and the displacement vector. So we have to use another definition of dot product. I hope you remember that. So what's that? Okay, F dot delta r is equal to the magnitude of force times the magnitude of the displacement vector and times the cosine theta. So therefore, your cosine theta is equal to the dot product between these two vectors and the multiplication of these two vector magnitudes. Okay. Okay. So in the last problem, you already calculate f dot delta r. Yeah, here, right? You already calculate f dot delta r. Okay. So it's 1514. Okay, mega. Okay, so the other thing, what's the magnitude of force and what's the magnitude of displacement vector? Okay, the magnitude of force actually is simple. If you remember in chapter 2, what do we calculate magnitude of vector? So it's just 1.2 mega square plus 2.3 mega square and square root. Okay, and the other displacement is 380 square plus 460 square and do a square root. Okay, what's the answer? Let me try 1.2 square plus 2.3 square and do the square root. So 2.59. 2.59 mega. And what's the answer for this? 380 square plus 460 square and square root. So it's 596. So let's take 596. Okay, let's take 596. Okay, so it's 2.59 mega times 596. So what's the answer? What's the cosine theta? So mega can be cancelled out. Okay, so 1514 divided by 2.59 divided to 596. So the cosine theta is equal to 0.98. So it use the arc cosine. So what's the theta? Arc cosine 0.98. So its theta is 11.47 degree. So the angle is very small. The angle is small. Yeah, that's what we want. That's what we want. We want to the force and displacement is almost parallel to each other, and that's why you can do the maximum work. Okay, if your angle theta is large, and your force vector and displacement vector has a large angle, that you cannot do the full 100. So that means your work is not 100% on this ship. Okay, your force vector and displacement vector is parallel to each other. That's what we want to. That's the optimum, or that's the extreme goal we want. Okay. Okay, I just start the video here, and the next video we are going to a little more complicated case. Okay, because because if we're using calculating the work by F dot displacement vector, and this is for constant force, but sometimes your force is a function of displacement. In that situation, you cannot use only this simple formula to calculate work. You have to use the integration So we will show the example on the next video. So I'll see you in the next video. Bye bye.